first. So this is the website that you go to, and then it will ask some access code, and then you can enter KUDL, Korea University Deep Learning. Yeah. Oh, and also, please enter your student number, student ID number, not your name. Okay. So when entering the quiz, please use your student ID number only, not the name.
나중에 그냥 대문자가 되고.
And also, please don't do cheating at all, okay? So cheating is really a serious crime, okay? And I'm quite strict on the student who does cheating, and also in the previous semester. Some students didn't attend the class, and then just by the time of our class starting, and then someone just enters that website by entering the code, and then took the quiz. Please don't do so. I'll just randomly check and match physically present students with the list of the students who took the quiz at that day. Okay. So if you happen to do that kind of cheating of remotely taking the quiz, and then you will get immediately F, okay, for your grade. So and again, when entering your name, please enter your student ID only. I mean the number, not your name. Okay, and also, while taking the quiz, our class videos will be posted on the YouTube. So if you missed some parts of our lecture, and then you can go to this playlist thing. So I already uploaded the last class's video. And also, you can just search. I'll just post a link to that playlist. But you can just go to YouTube, and then just enter my name in English, and then you will see this kind of 2018 and second semester. And also, among those playlists, let's see. Yeah, we have also the lecture videos of the previous year's course. I mean, the same course was open last year, and then I also posted most of the class videos. And then it was the class was run in almost the same manner, just as a flipped class where you just watch the CS231N and then post your questions, and I'll explain on these questions, and also and so and maybe good thing about it is that it was taught in Korean, so so it is actually in Korean. So whether you like it or not, you can actually utilize this resource as well. Does anyone need more time? Okay, I'll probably close the quiz maybe in the next 3 or 4 minutes. Before starting the class, any questions? And also, regarding the next week's class, we will cancel our class. Okay, so I thought of preparing for some programming kind of sessions, but I think it's too early. But instead, I will give you some video lecture link so that you can kind of self-study. So you are already doing the self-study for the CS231N. I understand that, and also I want you to study some of the lecture videos that I posted, okay, which is like additional or helpful kind of material that can then they can help you understand what we are currently studying in a better manner. Okay, and so again, this is slido.com, and then the access code is the same, KUDL, and then you can post questions over here, or you can just feel free to raise your hand and then ask the question. Okay. Again, the term project is at a team level, so you can form the team up to maybe 3 people, including yourself. Okay. Although you can of course do the term project individually by yourself. Okay. And quiz, mostly it's a really simple answer or multiple choices where you don't have much opportunities to just enter Korean. It's not like describing your answers in detail, right? As you can see from the first quiz that you just took, it's just composed of quite simple questions. Okay. I don't know who is Andrew, but technically, it's different, but practically, I will not check the attendance quite often. Maybe just a handful number of checking the attendance. So you can think of these quiz are working as kind of a attendance check. But as I mentioned, don't do cheating on just taking the quiz. If you are absent or you don't attend the class, and then just give the quiz up. Okay. Otherwise, if you do the cheating, and then you might get really, danger in getting F, immediately. Okay. Okay. Before addressing these questions, let me just try to do this kind of example again. I don't know why it didn't work, but it seemed to work quite well. Yeah, when I got back and then tried it. And so, see, we can immediately see it is forming the decision boundaries quite properly, right? And also, yeah, so there is no regularization, but in the case of an activation, yeah, it should be, yeah, selected as it should be sigmoid. Okay, so in that case, we are using 4 input variable and then linearly combining them and then passing it to the logistic function or sigmoid function. So that's what this means. Okay, so in this case, so yeah, in most of the cases, yeah, it's just performing really immediately. Okay, and then let me just refresh this like this. Okay. So what are these? What are these initial kind of figure? Okay. So these are the decision boundary and the prediction scores based on the current random initialization, right? And then let's think of the form of some kind of random initialization. So if you remember the class last time, it is just composed of a linear combination of those 4: ax1, bx2, and cx1 squared, and dx2 squared, plus e, which is our bias term, right? So that is our decision boundary, making it equal to 0, right? So by just changing some of these coefficients, yeah, we can actually, we can represent a quite rich kind of set of curves, right? So by just setting the coefficient for these, we can have a linear decision boundary, of course, right? And also by setting those coefficients as 1 and 1, okay, 1 and 1. In that case, what would the decision boundary be? It's a circle, right? What if we have maybe different positive numbers but different numbers, maybe 2 and 3 as a linear combination coefficient? In that case, it's an ellipse, right? Ellipse. What about having maybe negative 2 and positive 3? Right. So that's what is the name of that curve? 뭐라 그러죠? 한글로는 쌍곡선이라고 하고, 이게 뭐더라? 영어로 하이퍼볼릭 뭐였죠? Okay, so yeah, this kind of thing, right? Yeah, and also, what if we have, one of them as 0? So only one of these second order term being non-zero, and the other one is 0. In that case, 또 까먹었는데, 포물선? 네. 포물선 이렇게 생긴 거 알죠? 네? Quadratic curve? Yeah. Is it? I thought all these cases are called, belongs to the category of a quadratic curve because they are just a quadratic function.
Yeah, you're right.
Yeah, not sure. Yeah. Okay, so that way, by adding just simply the 2 additional kind of feature augmentation of x1 squared, x2 squared, we can have much richer set of decision boundaries that we can represent by our model. Okay. Okay, and then it's rarely happened, but I found that in some of these initialization, like this. Okay, so in this case, it's just a plane or currently being trained, but it's not properly learning the decision boundary, right? What's the reason for that? I mean, what's the phenomena related to that? So what caused that to fail to learn the decision boundary properly? So that is because we started with the bad random initialization, and thus that's like we got trapped into the bad local minima. Okay. Right? So you guys know kind of convex or non-convex functions and things like that. Okay. And then, yeah, one more thing here. What if we set it as a linear? What if we set it as a linear? So in this case, although it looks like, yeah, being properly trained, right? So it doesn't seem to matter whether we have a sigmoid or a linear. Oops. Okay, so in this case, so after we aggregate or combine them as a linear combination, okay, and then in terms of this nonlinear unit, in the case of linear as a nonlinear unit or this activation function, and then it means we don't actually apply any additional nonlinear functions or nonlinear units. So the output should be just a linear, yeah, linear combination as just the final output, okay? So in this case, what would be the problem? I mean, although it doesn't seem to have any problems here, but in this case, it's generally not not recommended. It's not proper kind of application of our machine learning model. And why? Can anyone give a reason? So what's the issue here?
You have to modify input features.
Input features?
Polynomial, something other than x1, x2. In this case, we use x1 square and x2 square, so we use the activation function, linear activation function, but we can find way of x1 square and x2 square so that we can circle boundaries.
Right. Yeah. So basically, when just looking at the linear combination equation or form, linear combination form, yeah, we have no problem of forming this circular decision boundaries and so on. But that nonlinear, I mean, the activation unit is just applied to the final output of this linear combination, right? So it's a related, yeah. So my point that I'm trying to make is related to like the task setting or problem setting here. So it is basically a classification problem, not a regression problem, right? So all these all the possible class labels or output ground truth values corresponding to our output is either 0 or 1, right? So if we just use a linear combination as our final output, okay, and in that case, in general, our y values will be ranging from -infinity to +infinity, right? And so why do we, so I'm talking about like the story where we move from a linear regression to logistic regression. What was the problem? So if you remember, I mean, if you watched or studied the Andrew Young's linear machine learning course, and then let's see. There is a logistic regression. Yeah, it's a little bit dirty, but so yeah, if you watch it, Andrew Young's machine learning course, and you might remember this example. But yeah, so this one is the example where we have only one input feature. And then, including the bias, our linear model will be just y equals ax equals b, y equals ax plus b, and we will form the line, and then we have to fit these corresponding y values into the given ground truth y value, right? But in these cases, they are either all zeros or ones, right? So in this case, like the decision boundaries are formed around here. So if it is less than this value or less than this value, and then it will be classified as a negative. And if it is larger than that, and then that corresponds to decision boundary over here to the right, and then right. So So if we have one example over here, which is really clearly positive one, and then this linear decision boundaries, I mean linear model should be like it should be like this, so that we can fit between this value, which still have the ground truth y value as 1, but in the case of a linear output, I mean linear combination output, it can go to easily like positive infinity, right? So in that case, our model is saying this data item is really, really positive, but that positive value around over here, that should be like suppressed, right? So that way we introduce sigmoid function, right, or logistic function, right? So in that case, the decision boundaries may not be properly learned. So in this case, the same problem will exist, right? So basically, by applying logistic function, we have to set the bound of our output from the linear combination as between 0 and 1, right? So it's related to like logistic regression. So if you are not understanding what I'm currently talking about, then please review this linear regression and logistic regression more carefully. Okay. Any questions so far? Okay. There's another Jaguar tree here. I'll send an announcement later, maybe in a week or two. But roughly, you can form the team maybe until this month. Okay. Okay. So let me briefly go through our slides. First of all, we mainly learned about different loss function in this chapter 2 and 3, right? And let me just point out one really global rule that you have to keep in mind, although it's quite simple. The loss, can the loss be negative? So is it possible that your loss value at some point or at any point be negative? So it is not, right? So when talking about the loss, right? So it is always greater than or equal to 0, right? So if you see in any cases while doing the programming or when doing some exercise or solving some problems, if you see negative loss value, and then it means something is wrong. Okay, whether you have some bug in your program or in your calculation. Okay, and then let me just discuss first about this k-nearest neighbor classification, because that comes first, right? Okay, so let's see. So have you played with the k-nearest neighbor demo in this website? Let's see. No, not this one. So I think you guys all know how the k-nearest neighbor classifier works, right? And then here a few points that I want to make here is So this is the decision boundary when the number of, the k value as 1, and then 2, 3, and 4, and so on. Let me just, okay. So I'm just gradually increasing the k value. So what is the white region here? For example, like this. What's the white region? Does anyone know? Can anyone guess? 네? 바운더리? 바운더리가 이렇게 두꺼워요? 네? No majority. Yeah, right. Yeah, right. So it's the case of having tie scores, right? So you know how k nearest neighbor classifier works, but that white regions are corresponding to having the two or more classes having the majority scores or majority vote, right? Okay. So if we had maybe k as 5, and then what's the region for this? And then the possible tie scores are like the two of the classes have gotten or received the 2 votes among 5, right? So it's like 2 and 2 and 1, right? So those regions are corresponding to that. And also related to that, when typically using k nearest neighbor classifier, so let me just show the example. So between 2 and 3, which one has a wider or larger white regions? It's basically, 2 has larger white regions, right? So if we use even numbers as a k, and then the even number, initially the even number will have a higher chance of getting multiple tie scores, right? So that way, we typically use an odd number for our k value, for k nearest neighbor classifier. But as we saw in the case of k being 5, we cannot avoid entirely those tie scores, right? So even if k is set as 3 or 5, we will have those some white regions, although it is relatively smaller than the case where we have an even number. And also another point that I want to make is, so you guys know the overfitting and underfitting stuff, right? And let's see. Overfitting means we almost perfectly fit our training data, but not much on the test data, right? And then underfitting is the case where we didn't even properly fit the given training data, right? And so what about the bias variance? So overfitting corresponds to high bias or low bias. I mean, if one is high and then the other will be low, right? But anyways, so this one is first and this one is second. So let's just do the poll. The first one, high bias corresponds to overfitting, or low bias. Okay, so overfitting means it has a low bias. Okay, so you can think of this bias as the degree of fitting your training data, right? That you know the label about, right? So training data, the label is known, right? And then the degree of how much you fitted your training data using your model, that is corresponding to the bias. But there is a kind of a sweet spot when in terms of degree of how much you fit your training data using your model. So if it is too much, and then although you had a really maybe if I explained in an opposite way, sorry about that. But if you fit your model very well, I mean, if you fit your training data very well, and then it corresponds to low bias, right? Low bias, which means the low bias means you fit your data or training data very well, right? But if it's too much, and then it actually turns into a bad thing, and then that's when this variance term start to increase, okay? So, yeah, so if you fit your data overly or too much, and then even though you have you achieve the zero bias, but you're starting to get higher variance, okay? So both of them are not good, okay? So both of, neither of them are not good one. And so we have to minimize both of them, but if you minimize bias too much, and then you will get high variance as well. And so overfitting and underfitting, so we have two cases. And then what is the case corresponding to K being high or K being low? For example, K being 10 or K being 1. Is it like this or is it like this? So this one, and then the cross one being the first one. The second one. Okay, so first one got more votes. First one got the more votes, right? So we have to so the task is to figure out, determine low K is bringing overfitting or high K value is bringing the overfitting, right? So let's see. It doesn't have K values. Let's see. Okay. Let's look at this. Okay, it doesn't have K values either, but yeah. So which one do you think is lowest K value? The left, upper left one or the right bottom one? I mean, which one has the lowest K value? Upper left, right? Upper left, right? And then if we have larger K values, I mean, like the region around the decision boundaries, right? So the behaviors will become different depending on different K values, right? So this is corresponding to the K being the lowest as 1, for example. And then if we have large K values, and then we have kind of an effect of an averaging out, right? Averaging out. So for whatever regions or whatever positions, if we consider a large number of nearest neighbors and their majority voting, and then we will roughly get the consistent kind of predictions, right? So it doesn't really change much on our decision boundaries, right? So in that case, it is corresponding to kind of underfitting, like a simpler model, right? And then this one is like an overfitting case. So for example, in this case, so in the case of K nearest neighbor classifier, we can even think, we can also still think about the training accuracy. Okay, training accuracy. So in the K nearest neighbor classifier, there is no really separation between the training phase and the testing phase. So in this case, including myself as a candidate for the neighborhood, if we use K as 1 as a K nearest neighbor classifier, and then the nearest neighbor will be always myself, right? And then the result of the classification will be always the same as the label of myself, right? Right. But if we consider the neighborhood, and then even if I am a positive classes, but if 2 of my other neighbors are all negative classes, and then when doing the majority voting, and then I will be classified as a negative one, which is which is obviously different prediction result from the known training data, known training label of myself, right? So that way, if K is larger and larger, and then I will get influenced more and more by my neighbors, which may have a different labels from mine, and so yeah, we cannot fit our data properly. Okay. Okay, so that was about the k-nearest neighbor classifier. So yeah, this CS231N discusses about the regularization in terms of an L1, L2, and their combinations, which is called the what? What's the name of the regularizer that combines both L1 and L2? So I should have included it in our quiz, but what was the name of it? What's the name of it? Huh? What's that? Yeah, elastic net, right?
Are you answering the questions? Are you answering the questions?
Kind of.
Can you translate it for us?
Oh, I see. Oh, I see. Yeah. Okay. Yeah. Yeah, I'm looking at this second one. So that is. Yeah, I didn't expect to translate it into English, but it's saying L2 regularization. Yeah, the lecturer said that L2 regularization is diminishing all the weights of our parameters kind of equally, right? So yeah, the question is how do we understand that mathematically? Okay. Okay, so yeah, where's elastic net? What's the page number? Can anyone give a page number? 34요? 지나갔나 보네요. 여기? 아, 렉처 3에 나와요, 이거? 아, 그래요. Okay, so if we use the L1 and L2 regularization, and then it is called the elastic net. Okay, and then let me just explain a little bit of the effect of the regularization, which suppresses your parameters of your model. So if you have, for example, AX plus B, and then suppose we have a training data as maybe X1, yeah, the first training data is maybe 1, and its label as maybe 3, for example. And then suppose the current A and B. So we typically randomly initialize those two parameters, right? As maybe 2 and maybe 2. Okay. And then what is our training loss in terms of least squares, or yeah, this kind of squared loss. And then AX plus B minus Y squared. So that is our loss function. Yeah, when it comes to just considering just a single data, right? So in this case, let's just yeah, plug this into here, and then A times 1 plus B minus 3 squared, right? So this is our loss function, right? And then, yeah, I assume that you guys are kind of familiar with the gradient descent. So I'm trying to show how the gradient descent works in this really simple example. Okay, so so this is our loss function, and then we have to come up with the derivative with respect to A and B, right? So in this case, so let's just apply the chain rule, and then it's like A plus B negative 3, and then yeah, let me just change A as 2, okay, to make this example more interesting. Okay, and then let's see. So in this case, what will be this number? I mean, we are computing the partial derivative with respect to A. What's the number? 2, right? So it's like we apply the chain rule. So that being the big variable, and then it's like x squared, and then if it is a we compute the derivative, and then we will have this, and then we go inside of this x, right, large X, and then we look for our variable, this variable, and then the derivative will be 2, right, and so that value will be further multiplied, right. So this is how this chain rule works, right. So this chain rule is really, really important, by the way, in order to understand properly the backpropagation, which is really the key kind of idea to optimize whatever types of neural networks or deep neural network models. Okay. But anyways, so this is the function of this partial derivative, and then from here, the current a value is 2, right? So let's plug this guy over here. And then we also need a b as well, right? In order to compute this partial derivative with respect to a, right? So even though we compute the partial derivative with respect to a single variable, a, right? But still, the function of this partial derivative may involve all the variables that you have. So that way we have an a and b. Even though b is considered as a constant, but still b can survive in the form of our gradient function. Right? Okay, so let's just plug that in, and then it's the 12, right? So this is the gradient with respect to a, right? So how do we update the value of an a? So a is currently 2, and then we just use the negative sign. That's why we call the gradient descent instead of gradient ascent, right? Because we want to minimize or lower our objective function, right? Okay, so if we need the step size, and then let's just set the step size as 0.1, which is our hyperparameter, right? So it should be set in advance. And why do we use that value? There is no reason. I mean, we have to optimize that value as well by using our validation set, such as like cross validation and things like that, right? But anyways, let's just suppose we currently use the step size as 0.1, and then like this, right? And then the value will be 0.8, right? So this is our newly updated a value, right? So this is just showing just one simple example of gradient descent of a particular variable that we have. So we can do the same thing on the b by just computing the partial derivative with respect to b, right? Okay, so far so good, right? Okay, and then let's consider the situation where we have a regularization over here, and then the regularization is put over here, right? And then in the case of an L2 regularization, it is like this, a squared and b squared, and then maybe some hyperparameter. And then let's say our hyperparameter as 1/2, okay? Okay, so in this case, what will be the new partial derivative with respect to a for this newly defined objective function? So in this case, because these two functions are added together in our objective function, so partial derivative will be still the sum of the two partial derivatives, right? And so the first one will still remain the same, and then what about the second one? So what's the partial derivative with respect to a over here? So it is like 2a, right? 2a. So we currently have an a as 2, and then this was the gradient that was produced by just trying to minimize our loss function to fit our data, right? Fit our data. But to minimize this part, which is our regularizer or regularization part, and then we additionally get this amount of a gradient, right? And then a is currently 2, right? And then what is the gradient? It is 2, right? Currently, right? So let's just use a little bit smaller regularization. Okay, I think it's too much, but anyways, the regular, the additional gradient that we get is 0.5 by just considering this as well, right? So 2 and 0.1 and 12 and plus, like this, right? So, so it's like, 2 was moved to 0.8, right? Yeah, due to this gradient part, right? But at the same time, we have an additional gradient part, caused by this regularization, right? And then let's think of the sign of this gradient, the sign of this gradient. So if a was 2, which is currently the positive value, and then its partial derivative will be always represented as this. So if a is positive, and then that part is also positive, right? So it will have the same sign. So a is currently positive value, and then its gradient value for this regularization term will also have the same sign, right? Positive, and then gradient will also be positive for the regularization part. So positive and also positive, and then we always subtract, right, this gradient from the original value, right? So that means if we have a positive value, and then positive gradient is subtracted from the original value, and then that gradient will be always produced so that your value is moving towards 0, right? So let's think of the opposite case where we have maybe a as maybe -3. So that is current parameter value, and then this gradient value will be also having the same sign, the negative value, and then we subtract the negative value, and then we actually add some positive value as well. So in that case, we have, we also move this current value towards the 0. Okay. So like graphically or pictorially, we think of this kind of a one-dimensional number axis. 수직선이 영어로 뭐죠? 네? 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 버티컬? 버티컬? 이 수직 이거? 그거 말고 이 수로 이루어진 직선. Number line. Okay, number line. Okay, yeah. Okay, so let's think of 2 being the current value, and then what is the force or the gradient due to our L2 regularizer? It's like this much, right? So that is coming from like one. This is really the hyperparameter that we set, right? Assigned to the L2 regularizer, but this part is really the important part, which is the form of the derivative of this regularizer, right? And so it is basically proportional to a, the current value a, and then the direction will always towards the 0, right? So if your current value is here, and then you will have this force, which is your gradient, and then suppose you currently have here, and then you will have a bigger force, right? But still the direction will be towards the 0. But what if we have the current value over here, and then proportional to this length or this absolute value, the magnifier, the magnitude of that gradient will be proportional to the current value a, but still the direction will be towards the 0, right? So that way your regularizer will always move, will always give an additional force to move your current value towards the 0, okay? So that way we are kind of suppressing all the parameters, right? But in this case, let's think about the L1 regularizer, okay? L1 regularizer. So in this case, our L1 regularizer will be replaced as this, right? So this is a definition of an L1 regularizer, right? And then let's think of the force, which is really the gradient value. So because we consider just a gradient with respect to only one variable, so let's just ignore this part and then consider this something like this, okay? So in this case, what is the gradient? So geometrically, so it's like this, right? And so yeah, although the derivative is not defined at the exact point of 0, but all the other points we can, the gradients are defined with no problem, and then the gradient values will all be the same as what? 1 or -1, because that is like a slope of a tangent line, right? And that tangent line is the same as the original line, right? And also it's like mathematically or like this function is like x and minus x if x is greater than equal like this, right? So if your x is currently like a positive value, and then what is the derivative of it? It's 1. What is the derivative? -1, right? Okay, and then let's just consider this in the context of optimizing your variables through this gradient descent. And then your current value is over here, 2, right? So in this case, we will have this force, but what if we our value is 3, and then what is the force and the direction of that gradient due to this L1 regularizer? It is really the same as this guy, right? Because it is no longer be proportional to the current A value, right? Right? 네.
한국말로 질문드렸어요.
네네.
0에 가깝게 한다는 게
네.
에러, 그러니까 로스를 0에 가깝게 하는 게 아니라 A나 B를 0에 가깝게
네.
하잖아요.
네.
그걸 0에 가깝게 하는 게 좀 더 노멀한 그 경계가 나온다고 하는 걸 어떻게 알 건지.
아, 노멀한 경계요?
레귤러리제이션을 하는 이유가
네.
좀 더 노멀한 경우를 찾으려고 하는 거.
노멀하다는 게 어떤 뜻이에요?
좀
부드럽다?
네. 되게 오버핏돼 있는 경우를
네.
찾지 않고
네.
그것보다 좀 덜한 경우, 표현을
네.
어떻게 해야 될지 잘
네네네.
모르겠어요. 그런
네.
거라고 알고 있는데.
네네네. 그러니까 이게 so let's just think of like this kind of case, AX2 and maybe BX. It's like example that we considered. X2 and CX1 squared and DX2 squared and E equals 0. So we guys understand that, understand this one can represent all the various complicated decision boundaries, right? So in this case, those A, B, C, and C, D, and E are our learned parameters. But if they are close to 0, and then their kind of curvature is not really like dramatic. So for example, like 1 and 2, maybe 1,000, and maybe 500, and so on. And then in that case, it is really like showing complicated decision boundaries. Although I'm not showing the actual examples, but potentially or generally, if we allow our parameters to have really large magnitude, and then altogether their linear combination or this kind of overall formulation or overall equation may become really complicated decision boundaries. But if they are all close to 0, and then they are like a little bit smooth and the curves that doesn't have really dramatic changes.
비슷한 맥락에서 사실 전부 다 0이 가까워질 필요는 없을 것 같은데
네.
예를 들면 이 같은 경우에는 0이 아니더라도 드라마틱하지 않을 수 있는 그런 경우니까 꼭 전부 다 0으로 해야 되나라는 의문이 들어요.
Yeah. Right. So he's asking about the potential way of assigning different amount of forces for different variables. So for example, in this particular case of a regularization, they will get all the, fair, not equal amount, but we treat them fairly, right? So if A was 2, and then that corresponding force will be the same as the force that B will get when B is 2, right? So if A and B are currently the same value, and then they will get the same force, right? But what if our situation may require some some subset of our variables to have a less force than the other, right? Or some other variables may have a higher force, right? So in that case, usually when imposing the regularization of an L1 and L2 regularization, we do not know which variable to put more forces in terms of a regularization in advance, right? So we just give the same force, same amount of force, and then we let our model to find the optimal kind of solution based on that. Yeah. And also, in terms of the amount of forces, I mean, I wanted to emphasize or point out this kind of thing. So as we saw in here, so in the case of an L2 regularization, the forces the amount of forces will be proportional to the current absolute value or magnitude of the current parameter, right? So if it is really away from the zero, and then it will get really strong force, right? So it is really the same as like a spring thing, right? F equals kx. You guys remember that? F equals kx. Yeah, so that is really the same thing. But anyways, so that's the property of L2 regularization. But in the case of an L1 regularization, regardless of any positions, even though the direction may change. So if it is a left side of the zero, which means currently it's a negative value, and then the direction of the forces will always towards zero, right? If it is positive, and then it will it will produce the force towards the zero. So that is the common aspect or common thing or properties, but the amount of force will be different. So suppose currently we have our parameter value over here, and then over here, and then the force due to our L1 regularization will be the same, right? Because that is just representing that's the constant, right? So let's think of the two variables, A and B, and A is currently 2 and B is currently 5, for example. So in this case, the regularization will really push this guy towards 0 with a large amount of force, and then this guy will have small force, right? But in the case of a L1 regularization, this force will be the same, will be the same. And so in that case, I mean, you guys probably have heard that L1 regularization will often give you sparse solution, right? Sparse solution. Sparse solution means some of your parameters in your model, even though maybe you used this 5 parameters as your optimization variables, and while doing the optimization, some of them will eventually become 0, right? So maybe 3 of them are 0, which has the effect of not using these variables at all from the beginning, right? So that is a final solution, and that is called the sparse solution. Okay, you guys know what the sparse solution is, right? So some of them are exactly 0, right? Like 3 of them are 0. So that is called the sparse solution, because only 2 of them are non-zero. So non-zero values are sparsely found. So that's the meaning of the sparse solution. So in this case, so if we exert the same amount of force, regardless of their distance from the origin or 0, and then eventually some parameters will become easily just a 0, because we just put the same amount of force. But in the case of L2 regularization, even though this guy will have really large force, but suppose your variable is maybe A value is a 0.001. So in that case, in proportional to that value, the forces will also be really minimal or very, very small, right? So in that case, it will almost have no forces, and thus it will just remain as that value instead of just becoming exactly 0, right? So that's the reason of getting the sparse solution in the case of an L1 regularizer. So some student had a question around here. Is there any questions
about the project? What kind of subject going?
It's just 3 topics that you choose.
anything related to vision or maybe also natural language processing?
Yeah, and even speech, and maybe other time series data or any kind of data.
Okay.
Yeah, as long as you use neural net and deep learning and so on. And it doesn't even need to be really deep. So, so yeah, as we will study, maybe probably that will be, I'm not sure, but yeah, that will be part of your self-study kind of, that watches the video lectures as well. But I plan to cover some of the word embedding stuff. And yes, something called the word embedding is just literally using the 2-layer neural net or just a 1 hidden layer neural net. So in that case, we cannot really call it as a deep neural network, but that's really the popular techniques. Used together with all the complicated deep learning models. So that's quite important. Any other questions? Okay, so I believe this question about the L2 regularization was covered, right? If not, please, explain again your questions. Okay, so. Regularization for, so what if the hyperparameter assigned to the regularization term is the negative? So we don't consider that, okay? So again, loss is always positive or greater than or equal to 0, right? And so, in case your loss is composed of multiple different terms. So in the previous examples, we have the term corresponding to the data fitting and then the other term corresponding to the regularizer, right? And then each of these terms should be non-negative. And they should be combined by using the positive hyperparameter, positive weights, okay? So at least, as far as, my knowledge goes, I haven't seen any kind of cases where we use negative kind of thing, okay? Although, some terms may be kind of a negative value. So, so it will be covered, it might have been covered or will be covered in some of our video lectures of this CS231N, but what if you want to maximize some measure? So you want to maximize something, but we always represent it as a minimization of our objective function. So in that case, we just put the negative sign of the term that we want to maximize, and then and then we can minimize that. And that is equivalent to just trivially equivalent to minimizing maximizing something is equivalent to minimizing the negative something. Okay, so usually this is not considered. So you can just safely ignore this case. Okay. So in the hinge loss, okay, so it's there's a hinge loss. Okay, so the reason why the margin in the hinge loss doesn't matter is, let's see. So this is called our margin, right? 1. And in the case of support vector machine, we just use the margin always as 1. And that's because that margin value, as long as that value is just a fixed value applied to each of our data items, for different sets of these prediction scores, if as long as we use just a fixed margin value, and then the actual value of that margin, that fixed or common margin value doesn't matter, because as we saw in this somewhere here, so in this case, what is the hinge loss in this case? So how do we compute the hinge loss? So for this given image, and then these three are the class prediction score, right? And then there will be the score corresponding to the ground truth class. And then here, this one has the ground truth class as a car, right? And this is the score that we want to focus on, right? And then we compare this guy with all the other classes, which are sometimes called the negative class. Okay, so for this image, this is a positive class because that is really the class of that class. And then these are not true one, so that is sometimes called the negative class. So for the single positive class, and then we compare, we compute the score differences between this a single positive score with each of our negative class scores, prediction scores, and then compute the difference. And then if that difference is always greater than or equal to 1, I mean, if this one is greater than each of these values by the amount of 1, which is called margin, right? And then that's when we have zero loss, right? So we are perfectly happy. Okay, but suppose we have the difference as 0.5, for example. I mean, yeah, so in this case, 4.4. So in this case, we didn't satisfy the margin yet, right? So in that case, the loss is what? 0.5, right? 0.5. 네? 그러니까 요 두 개는 로스는 0.5죠? Yeah, okay. So in that case, yeah, it didn't clearly satisfy the margin that we set as 1, right? And yeah, the trivial and the easiest way to increase this margin is just by scaling up our linear combination coefficient, right? Linear combination coefficient. So somewhere around here, yeah, it mentioned about like just multiplying the optimal coefficient or weight parameter W by 2. And then all the differences among these resulting values will become twice, twice, right? So suppose we have a particular W that produced all these scores, and then suppose we now use 2 times W as our parameters, and then all these scores will be doubled, and then this margin or 0.5 will now become 1, right? So that way, so that particular value of setting the margin as 1, I mean, the value of 1 doesn't really matter.
What you said was if you multiply 2 to the weights, right, then the loss remains the same. Is that what you're saying?
No. So yeah, although it's a quite special case, but let's just consider like perfect case where we have all zero loss. Okay, so so in this case, this value is greater than each of these two values by the amount of at least maybe 0.5. Okay, so if we were set the margin as 0.5, and then let's suppose the current situation has zero loss. Okay, so that means at least our positive class score is greater than all the negative scores by the amount of 0.5. Okay? So in that situation, the loss will not be 0, right? If we just consider our margin as 1. Right? Does it make sense? But in that case, we can just we have just a really simple way to make that situation to become, to have the zero loss. And how? We can just simply multiply W by 2 and then use it as our parameter. And then all the differences will become 1s, and thus the loss will suddenly be 0. Does it make sense? 이해 가죠? 설명 다시 해줘요, 혹시? 한글로라도. 됐죠? Okay. So that, due to kind of this intuition, based on this intuition, in both, in SVMs, the margin value itself doesn't matter. So we just set it as some constant value. And yeah. Any other questions so far?
In the video, you mentioned that K4 validation is very useful for smaller data sets. Right?
Which validation?
K4.
K4, okay, yeah.
They say it's very useful for smaller data sets.
Uh-huh.
Can you explain why?
So yeah, let me say this. So when doing really like a serious task by using a deep learning, for example, you want to train your own model by using ImageNet data, which has maybe 1 million data items or images, and then you cannot do the cross validation. In that case, we typically use just a fixed setting. So where we have maybe 100 data items, and then we just split them into maybe 8 to 1 to 1, and then this is your fixed training data and validation and test data. So we just fix that setting, and then training and do the training and testing only once by using that setting. But in the case of a cross validation, it's like they are rotating with each other, right? So some parts are becoming training data or training part, and then sometimes it will work as a validation or the test data, right? So in that case, the main advantage of using cross validation is that you can so in this case, what is the number of data item over here? It is only 10, right? So our conclusion or our kind of evaluation or final score about how good our model is performing is only evaluated based on using like 10 number of data. Okay, 10 data is really small one, right? So can we rely on that result that was produced by using such a small number of data, right? So in that case, we may feel a little uneasy or uncomfortable, right? So in that case, the effect or benefit or advantage of the cross-validation is that, so we will get the prediction score for this, which works as our test data, and then this one will work as also the test data in some other settings, right? So in that case, if we just average out those prediction scores, and then our prediction scores will be based on the on using entire data items. So that evaluation or performance measure was evaluated based on the entire full data, right? So we feel a little bit more comfortable, right? But what's the price for doing so? It's just computation, right? So if we do the 5-fold cross-validation, we have to do the training and the testing 5 times, right? But if we just fix that setting just once and then compute the do the testing only on this set, and then it's just a one-time process, right? So cross-validation is literally taking the k times more computation than the fixed setting, right? So if our data has really many data items, and then we cannot do the cross-validation because it will take maybe a year, right? So only one kind of setting, it will take maybe, suppose it takes a few weeks, right? And then if we do the 10 cross-validation, a few weeks will be tens of weeks, right? So practically, it will be quite taking a long time. Okay, so that's why, that's how this small data is related to the cross-validation. But in practice, if we have really sufficient number of data, and then we don't do the cross-validation. Any other questions? Okay, so have you guys understand this figure? So what's the y-axis? So I want to really improve this figure, but this one is loss, right? And then so this what is the x-axis? So it is SYI. Okay, what is YI? YI is the ground truth label of I's data item. Okay, so here, what is the SJ? So for let's see. Okay, so let's think of this car case, and then yi is 2, because this has the label of this second category. Although if it's a 0 based, and then it will be 1, but if it is a 1 based, then it is 1 and 2. It's the second category, right? And then this S of yi is the score, prediction score, right? So let's just make it as our variable x, okay? Let's just suppose we have a freedom to change that value, and then now, but instead let's just fix j as 1. If j as 1, and then it will correspond to this, and then let's just consider that value as the pre-given value. So this value is 1.3, and then the real origin will be somewhere around here, right? I mean, here 0, and Sj is currently 1.3, and then our x-axis, which can have a different values, so that is corresponding to this variable. So if this guy was fixed as 1.3, and then setting this as a variable, and then if it is greater than or equal to 2.3, and then the loss becomes 0, and that is corresponding to this blue line. And then if it is starting to become less than 2.3, and then it will start to create some loss, some non-zero loss, and then that loss is like this. Okay. So it's a really simple one, but it's a little bit difficult to read. Okay, so the time's up. So I wish I had covered more, but we will continue the next time, but again in the next week we will have no classes, but instead I will just assign some other additional video lectures. Okay.